Hey guys, welcome back to Genius Learning. I want to look at another example on a conductor in the inner sphere surrounded by a material that has electric susceptibility, and I want to know electric displacement, polarization, bound charges, basically everything we can about it. So let's start off with electric displacement. Okay, we have some conductor in the inside sphere with charge Q. These are the radiuses A and B, and the outside electric susceptibility is the orange part. Okay, so this is just a 3D view opened in the middle. And so first let's do electric displacement vector. Displacement, okay, and for that we're going to be using what we've been using, which is Gauss's law. So D dotted with differential area, Q free enclosed, okay, and for the left side we're going to have two integrals, 0 to 2 pi, 0 to pi. We have dielectric, and then the Jacobian, r squared sine theta d theta d phi. On the right side, Q free enclosed. The only thing that's enclosed in that region is going to be Q, so we're just going to leave it as Q. All right, so this entire thing turns into d 4 pi r squared equals Q, and to simplify that further, we got Q is equal to 4 pi r squared, and this is in the radial direction. Okay, electric displacement. So there's two regions, right? So this is not describing the full electric displacement. All right, so again, this is like the general term, like we did in the previous example. So we need to describe each region. So let's do that. We got, for the region where R is less than A, so we're inside here, we're in the conductor, and we don't have any free charge there. We're gonna have D equals 0 in that region. Okay, and then here for R greater than A, so now we're in this material right here, we're gonna have Q, D is equal to Q 4 pi r squared. That's in the radial direction, right? So this is specific now to the different regions, okay? And so this is hollow in there, and this over here describes the electric displacement outside of the conducting shell in the inside. All right, so in the empty space inside of the conductor, nothing is going on. There's no charge, no moving, nothing. All right, and so this describes both. Now from here we can jump to, let's box this up here. All right, we can jump to electric field. So now let's look for electric field, and we can use electric displacement is equal to epsilon times the electric field. Okay, so let's rearrange that, and should I put it down here? Okay, let's put it over here. So E equals D over epsilon, right? And so this is the formula we're going to use, and we have to describe the electric field for different regions. Okay, so just like we did with the the electric displacement. So first, let's look at R less than A. Okay, so we're inside here, and what do you think? If D is 0, right, then E is 0. So E is going to be 0 in that region. Okay, so now let's look at between, R is between A and B. So now we're here in the orange part where we have this electric susceptibility, and we're going to write the D that exists in that area, which is the only displacement we have outside of A, right? We have electric field is going to equal this, which is Q over 4 pi R squared and epsilon. Right, and this is in the radial direction. Right, so we can leave this like this, but this epsilon is specific to the region that we're in. So for now, I guess we can leave it, but when we do the polarization next, we're gonna end up changing this. And we can change it now. So because we're in this region, let's go ahead and express it how it should be expressed. I'm gonna write it. I'm gonna write it right here next to it. So electric field is gonna be Q over 4 pi R squared, and I'm gonna change that epsilon into epsilon naught 1 plus chi E. All right, and so that describes the material, right, and the potential and the susceptibility properties by including the electric susceptibility value. So we're gonna take this as the more accurate description of the electric field within this region. So let's do that. Okay, so this is in the inside, this is in that middle, and now let's look at the outside. All right, so let's write the outside. Let's come over here. So we're gonna do R greater than B, so we're somewhere out here. And again, we're gonna have the same thing because we only have one displacement. Okay, so we're gonna have Q over 4 pi R squared, and then epsilon in the radial direction. And when you see epsilon, immediately you should think, where am I? What region am I in? So I can describe this epsilon, which is the absolute permittivity, correctly. So I'm all the way outside, and remember, when you're outside, chi is equal to 0. So chi E is equal to 0 in a vacuum, right, or outside of a dielectric. So all the way out here, chi is going to be 0, and so E, or epsilon, is going to equal epsilon naught. And so that's what we need to do here. This was this entire thing, but since we're outside, right, this is chi E is equal to 0 in the vacuum, and then we just have this equal to each other. So the correct expression for this would be with an epsilon naught, still in the radial direction, and that's our electric field. So these are 1, 2, 3 are the electric fields in the different regions. Okay, so we're gonna need that for the next part where we calculate polarization. All right, so now let's see. Let's use, okay, polarization. Hope I have space here. All right. So let's see, polarization, and the equation for that is going to be P is equal to epsilon naught chi E electric field. Okay, so we have electric field, and we have it for all three regions, and this describes what's going on inside the material. So let's plug it in. We got, for R less than A, we got polarization is equal to 0, because the electric field is 0. Okay, for let's jump ahead to R greater than B. So we did the inside, now let's do the absolute outside, right? Because clearly we can see that in a vacuum, chi is equal to 0. And so the electric field is going to be equal to 0. So if the electric field is equal to 0, chi is equal to 0, all this is equal to 0. So I meant to write this. Okay, so outside, chi is equal to 0, so this is 0. Inside, the electric field is equal to 0, and so the polarization, and the only part that has anything going on with it as far as polarization is going to be the region A, R, B. So the region between A and B, the orange part, right, where you have chi. And let's plug in what we have for that. So we have epsilon naught chi E from this, and the electric field for that region is here with the values of the dielectric constant. So let's put all of this here. We got Q 4 pi R squared epsilon naught 1 plus chi E. And this is in the radial direction. So I see that the epsilon naught can cancel. So let's do that. Epsilon naught. And let's maybe label these P's. So I'm gonna label this P1, this is 2, and this is 3, because this is the outside, this is the inside, this is like the middle. All right, and so what else can cancel here or group up? I think we should just leave it how it is. So now we got polarization in this region where R is between A and B. We got chi E Q. All right, and then we got 4 pi R squared 1 plus chi E. That's in the radial direction. Okay, so here, and let's probably box this up in a different color. So the only polarization effects that we had were within this region. Okay, and that's it for polarization. Now let's take a look at volume bound charge density. So volume bound charge, volume bound charge density. Okay, and the equation for that is going to be, let's keep everything in the same. So we're going to have rho B, so bound, negative gradient dotted with the polarization. Okay, so we have a polarization already, or the only one that matters and has a value, and we know that the gradient for spherical, or we should know, I got mine in the front part of my book, so I'm pretty sure that's equations that they give to you. So let's see what happens. We got rho bound 1 over R squared, partial of R squared, and then let's write the polarization in a different color. We got all of this, which is chi E Q 4 pi R squared 1 plus chi E, and we're done with that part. And I already see trouble. All right, I see that these r squareds cancel out. And so everything else is a constant we can pull out. We're trying to take the derivative with respect to r, and nothing in here has an r. So taking the derivative of constant means that this volume bound charge density is equal to 0. Okay? So volume bound charge density, because these two materials behave the way they do, nothing is bound, nothing is uniform here. So it makes sense. All right, and let's check now the surface bound charge, because something might be going on there instead of the volume. So let's see. So we got surface bound charge. Okay, and that formula, we're gonna have sigma bound is equal to polarization dotted with the normal evaluated at the surface. This part is important. It needs to be evaluated at the surface in order for you to get the surface bound charge. All right, so this is the formula we're gonna use. And before we evaluate it, which is gonna be real quick, let's take a look at something that tricked me when I did an example like this, one of my exams. So we got the sphere, and we got an inner sphere, okay? So let's say that we're just making a miniature version of what we have up there. This is the orange part. Okay, and I'm not gonna draw the purple part, I mean the blue part, but it's on the inside. So the part that you need to realize is this radius here is A, this radius here is B, right, from the center. And here, you're gonna have the radial direction is going outward from the surface of B. So if I'm on surface B, right, and I'm going to the normal of the surface, or outward, then I'm going in this direction, right? Because I'm not on the surface and going inward, right? There's dielectric, there's a lot of material in here. From the surface, I'm going outward towards the normal. And the same is for the inside. So now if I'm on surface A, right, I'm not gonna look in towards the dielectric material, right? I'm gonna look outward because I wanna look for the surface bound charge. And so if I'm on A, I'm looking this direction, right? Because this direction tells me what's going on here at the surface. Just like if I'm on B, I'm going this direction because that tells me what's going on here on the surface, not on the inside where I have this orange dielectric. All right, so if we're going inward like this, then we are negative r hat. So I just wanted to make that clear, that you can be on this surface here and pointing in the radial direction, and then when it comes to being on the surface of A, you have to look at where there's empty or like surface bound charge gonna happen. So it's not gonna happen inside the material, it's gonna happen on the surface of that material, which is inward. So it's a little tricky, but we're gonna use that right now to evaluate the surface bound charge. All right, so let's look at the regions that we're in. So for the inner, we're gonna call it the inner. We can call it surface A, surface B. So if we want, you know, if that's less confusing, we're gonna evaluate the surface bound charge at the polarization dotted with the normal. So the polarization, we know we have this entire thing, and dotted with the normal is negative r hat. So surface bound, we got this polarization, we got chi q 4 pi r squared 1 plus chi e. Okay, and we have r hat, which is good, and dotted with normal to the surface of A is going to be negative r hat. It's going to be inward. And so that means that we need to change this r here to A. So let's do that. So now we have, for the inner, we have chi e q 4 pi a squared 1 plus chi e, and these go to 1, or specifically -1, so we're going to just bring the negative out here. And now we have our inner surface bound charge. Okay, and let's do, similarly, let's do the outer, or B. So now we're going to go to B right here, and the only direction where we have surface bound charge is going to be outward, okay, in the radial direction. And so similar to this, right, our R, because the polarization is the same, our R is going to be evaluated at B, because that's now the surface. And instead of negative r hat, we just have regular r hat, so it stays positive. So we're going to have, let's do it in blue, surface bound of the outer is going to be chi e q over 4 pi b squared 1 plus chi e. Okay, and that is the expression for both surface bound charges. All right, so again, try to be careful when you're looking at different surfaces. If you're in a region where going inward doesn't make sense, right? You're not on the surface if you go inward, then consider the opposite direction, which can be in the negative. All right, and last thing we need to find, let me see if we have some room. I might need to get a paper. I don't want to make another video for this part. Let me just get a paper. One second. Okay, so just get a paper. Okay. So now let's do the energy stored for the dielectric filled capacitor here. So the energy stored for the dielectric filled capacitor. So now let's write the equation for that, and let's do it here. Make sure I can see. Okay, so the energy stored for the dielectric filled capacitor, we have W is equal to 1/2 integral of D dotted with E d tau. And the book I used had W. This can also be expressed as capital UE, which is what we used in the last example. So let's just probably stick with that. So capital UE is equal to 1/2 integral of D dotted with E d tau. So we'll go with this. So this is the energy stored, and we already have the displacement and we have the electric field for the regions that we need. So maybe let's put it on this side and look at these values here. So we got here UE, right? We're gonna do 1/2, and this is a volume integral. So we got 1, 2, 3, 0 to 2 pi, 0 to pi, and always the tricky integral. This one's gonna go from A to B. So these are outward, the energy ones. Okay, we have the displacement, the displacement, which is, let's see, we got Q over 4 pi r squared, right? And then the electric field in that region. So we're in the region where A is between A and B. So the R is greater than A, this one's good. And we need this, or this, or rather, electric field. All right, so let's leave this in this expression for now, but we know that we can write it like that. Okay, so for simplicity of this long integral, for a second I'm going to leave it with this E. So we got Q over 4 pi r squared epsilon. That's for the E, and then our Jacobian, we got r squared sine theta dr d theta d phi. Okay, that is plus we got 1/2, 3 more integrals. Okay, 0 to 2 pi, 0 to pi, and then here we got b to infinity. Okay, so now the displacement in that region is the same. We got Q over 4 pi r squared, and the electric field in that region outside, right? Chi is equal to 0, and so we have Q over 4 pi r squared epsilon naught, and then our Jacobian, r squared sine theta dr d theta d phi. Okay, so let's try to evaluate this, and maybe I'll use one more if I need to. Okay, so let's do the top one first. All right, let me try a different color here. We're gonna do this one first, okay? Let's take out and combine things and do stuff. So U, E, I'm gonna keep this 1/2 out front. I'm gonna evaluate the solid angle, which is 4 pi. I'm gonna take out the 2 Q's, they're squared, and I'm gonna take out these 4 pi's. So that's 16 pi squared. And then I have epsilon, okay? And this is r to the 4th, but we have an r squared on top, so we stay with the integral from a to b of r to the -2, right? Because there remains an r squared on the bottom, and dr. Okay, so that one is simplified. And now let's simplify this second one. So this is plus, and now let's look at this second one right here. We got 1/2. Let's see, solid angle, we got Q squared. Again, we got 16 pi squared. Epsilon naught can come out, and again we're left with r to the 2nd on the bottom, so we have to evaluate this integral here, r to the 2nd dr. Okay, so these are the 2 integrals we have. Let's further evaluate. Okay, so let's simplify the top part. What do we have here? We got UE. So this part here, let's see. This and this become 2, 16. Okay, so that's 8. And one of the pi's cancel. Okay, so for this first one here, we're gonna have Q squared on top. We have 8 on the bottom, we got pi, and we have epsilon. This integral right here is gonna be negative 1 over r evaluated from A to B, okay, plus, let's go here, and I think this simplification is the same, okay, yeah, so we have q squared over 8 pi epsilon naught, and this integral here is going to be negative 1 over r evaluated from b to infinity. Okay, so let's evaluate those integrals. Here, let's just write it separate. We're going to have 1 over b minus a minus, so it's plus 1 over a. That's going to be for just this. And then here, we're going to have negative 1 over infinity minus minus, which is a plus 1 over b. This is 0. So this is the only thing that remains. So now writing it all together, let's see what we got. So UE is equal to all this, so q squared over 8 pi epsilon. And let's just rearrange this. We got 1 over a minus 1 over b. And over here we got plus q squared over 8 pi epsilon naught 1 over b. All right, so we want to just simplify this further, make it look nice and pretty. All right, we got, just take the q's out, q squared, we got 8 pi in common, and that's it. So what we're left with is 1 over a epsilon for this part. If I distribute it into there, we got minus 1 over b epsilon. And then this last part was left with plus 1 over b epsilon naught. And I think that is it. So this is the total energy. So the energy stored for the dielectric field capacitor. Okay, so let's see. This equation we already know from the previous examples. We need to watch out for the surface bound charge, especially if we're dealing with plates or spherical capacitors. And what other little booby traps? I think that's it. This one's pretty straightforward. So this right here is kind of like what bothered me when I was doing it. And then just being careful how to integrate the energy stored. Here we're just going straight up A to B, right? And then from B to infinity. So we don't include the conductor because inside of it, nothing's happening. And so we need to start from A to B, which is the region right out here in the dielectric, and then outside to see what's happening. Okay? All right, guys, thank you. Hope you enjoyed it.